In this video we're going to have a look at a simple but functional game loop. So it's going to be a piece of code, actually it'll be a class, a thread that will run that on a regular interval will request that we update and draw our game objects. And it's really going to be the beating heart of the game, so we will update and draw and keep on doing that with a certain frequency each second. That'll be the number of effective updates or frames per second. And generally speaking, we try to get 30 or 60 or something of that nature of updates and draws per turn. Because we're running it on Android, we'll have a little bit of additionality to it. We'll have a look at this now. It's really just by way of a reminder. So for an Android app, we've got to bear in mind that there are several different stages of the life cycle that we can go through. And you can see some of them here where we create, we then start, we resume, which we have a fully running application at that point of time. We can pause it, we can stop it, and we can destroy it. Now that's relevant because these are the different states that our game can go through. And it's only really if we have a visible game that we're playing that we probably want to be updating and drawing the objects. That if the user moves away from the game, we've got a choice. We probably want to decide to pause the game. That will not do update and renders whenever it's not visible, and whenever the player returns, then we'll carry on doing this. So that's a good, sensible thing to do. It means when it's in the background, we're not wasting unnecessary cycles that the player's never going to get to see. There's one little other piece of additionality to this, and we can see on the slide here. When we think about a game loop, we get into issues of who does what and different threads of control. Part of our game loop will involve us going to sleep. So we will, let's say for example, we'll have 20 milliseconds to get everything done. Normally within the game, we'll get it done within that period. It may only take us 15 milliseconds. So we have 5 milliseconds left over before we want to start doing our update and draw again. What we do in that case is we request that a thread, thing that's running this, goes to sleep for 5 milliseconds and then wakes up and carries on. Now, anytime we run an interface like Android or Swing or any of these ones, there is actually a thread that's running there to service our graphical user interface. And that's the thread that's checking to see where the mouse is moving or where people are touching in terms of different touch events. And it's really important that that thread is as responsive as it can be. That if the user interacts with the interface, then we do something based on that interaction as soon as we can. So the last thing that we want to do is to take our thread, which is there looking at interfacing with the user, and tell it to go to sleep. That basically pauses everything, including how we detect and interact with user events. So we only get into a situation, which we have here, where we have two parallel processing threads. So these are two things which are happening concurrently alongside one another. And if we had a CPU with multiple cores, we may run one on one core and run one on the other core. What we will have in this is we'll have a main thread which is really interacting with the user and getting things from that. And alongside that, we're going to have a timing thread that'll be responsible for deciding when we do our update, when we do our draw, and those types of things. The piece of code that we will look at actually will be the timing thread that will kick off the process of updating and drawing. On the main interface, there we're interested in getting input from the user. So in our main thread, that's where we'll collect our input from the user, and ultimately it's where the things that we're displaying get to be drawn on or will become visible to the user. So we'll have that little bit of interaction between the two. So a way of showing you what is going to happen here, we'll have a look at the code. There's two files, which is part of the demo project that was sent out that are relevant to us here. One is game loop test, which doesn't really have much to it. It's basically the activity that kicks off the fragment. But all of the stuff that we're interested in is stored within our game loop test fragment, which is a type of fragment. And we're going to have a look at what we have within this. Now, first of all, we'll just run the thing. So we'll get a bit of a feel as to as to what is happening. So we have a bit of messaging appear here. Let me open up our browser. So inside this, we've got our demo window. I'm going to click on the game loop test. And when I do that, I will create this activity, Aladdin and Fragment. The fragment isn't going to display anything. It's going to be a blank screen. But it will create an additional thread that will do the timing. And I'm not sure, I think it's twice a second we set this for the demo. So 2 times a second it's going to update and draw, update and draw, update and draw. And by way of indicating this happening, we should see some messages appearing down in our logcat window. That's where we're logging things out to. So let me click on game loop test. It says running the game loop, check your logcat window. And under logcat, you can see here that we are having draw and update messages appear. And they're basically hooks, if you like, that we would have our proper update and our proper draw for game classes. Obviously, we're not doing the game yet. We're sort of putting in place the things that we need to have in place to build upon this. Now that's ticking away. If I was to go back into my game, and let's say I was to pause the game, I went out to the main menu. So let me click on that. Now you see we're out here in the main menu. If we look back in logcat, we were in update 67 was the last frame that we had drawn. And we got a message that we're pausing our loop. So because the game's not active, we don't carry on updating and drawing. And if I were then to go back to my demo, we will then resume our update and it carries on ticking. So it's a simple demo, but we want to have a look at how it manages that process. So let's go back to our code to do that. So there's only really one file we're interested in. It's our game loop test fragment, and we'll go down through this to see what different elements that we have inside it. First thing, the first most important property of it is that we're going to have an instance of a game loop. Now if I quickly scroll down, game loop, you can see down here, is actually going to be a class. So this is a custom class, it's an inner class, we're declaring it inside this one. We could have declared it as a separate class in its own, but for reasons of simplicity, I put it in the same class here as an inner class. It's private, so it's restricted to this. It implements the runnable interface, so this is something that can run in its own thread of control. So at the top of our fragment, we say that this particular fragment has a game loop. It will have an element that will run in its own thread of control. And it's going to be that's going to sort of tell us to update and to draw. What we have really in the rest is fairly straightforward stuff. We have an onCreate, an onCreate view, and we actually are making different roles and purposes to this. So for a fragment, onCreate gets to be called whenever the fragment's created. onCreate view gets to be called whenever we're displaying the fragment. So once we create the fragment, one thing we do is we create a new game loop. And I'm passing in a parameter 2 in this case, which is the target number of updates per second that we want to do. Now, a game running at 2 doesn't make any sense. Did it for slowing things down so you could see it ticking in the demo. Normally here we might pick 30, 60, something like that. On create view, we don't really do much in this here. We are inflating the XML description. It has a text view that we're getting, and we're setting text within this, basically to tell the user that normally the game would be displayed here. Go and look at your logcat window to see the messages appearing. So that's fairly basic stuff. For this one, if we want to get in the behavior where when we pause and resume the game, that we pause and resume the loop, we've got to put in hooks. So the on pause and on resume, they're the correct points inside the fragment to trigger action if the fragment is paused and then resumed. So what do? If we pause it, we go to our loop, which will be this other object running in its own thread, and we request that it pause itself. And then we log out a message saying, okay, we're pausing the loop, and then we do whatever we normally do. If we're resuming it, we print out a message. We go to this object and we ask it to resume itself, to carry on, and then we call the superclass method. So fairly straightforward. A few of the other things here, so for the sake of argument for this demo, we're putting our update and our draw methods in this one class. So everything is all stuck together in this one class. And we really want to branch those things out, but it'll do for a demo. We have a counter variable. It's declared to be static because if we sort of quit out and go back, it's just going to carry on remembering how many ticks of this update and draw we've done in total. We have our do update and our do draw. Now, normally these are the things that you would update all of your game objects that are relevant at this point in time. You would draw all of your game objects that are relevant at this point in time. So we're not really doing the game here. How do we update things? We log out that we're updating, and we give it the particular update counter that we're on, incrementing the counter in doing so. So that simply says, you know, update 1, update 2, update 3, and so on. And ditto for draw 1, draw 2, draw 3. So fairly straightforward. Interesting class in this one is our game loop, which implements runnable. So in this case, this is something that can run in its own thread of control. So let's have a look at what we have inside that. There's a number of properties. The first one is target frames per second. So this is what gets to be passed in through the constructor. It's the number of frames per second that we're going to try to hit, to maintain. The reason I say try is that if we're doing something highly complex or graphically very fancy, maybe we will put more pressure, more strain on the GPU and the CPU, so we can't actually maintain that target number of frames per second. So instead of being able to hit 60, I'm only hitting 53, 54, something like that. But that records our initial target. Here we have a thread object called render thread. Initially it's null, so we haven't yet got to create it, but this is going to be the thread, the separate process of execution that will do our timing on. We've got a Boolean flag called running, and initially it's equal to false, so initially we're not running it. You can see here that it's declared to be volatile, and that's important. If we go back to this diagram here, so because we have two threads, we have a main thread and we have a timing thread. My timing thread is my game loop, and it contains this boolean telling me whether or not this thing is running. And the reason it's declared to be volatile is that, sure, the timing thread itself might update its own state, but other threads, other processes running concurrent to it could come along and could change this themselves. So it's something that might change unpredictably. And because it might change unpredictably, we declare it to be volatile, and that basically puts a flag in that if you're caching this, you need to be careful because any cached value could change unpredictably. So generally it won't be cached. We have another, the last property here is target step period. And description of this, variable holding the duration in nanoseconds of the target game step period. So if we were to have 2 updates per second, then this would be, what, 450 million nanoseconds that we would have available to us. So this is just how many nanoseconds we have available to get our update and our draw done in. Right, constructor then. So when we're creating a game loop, we pass in the number of frames per second, we store that, and then we work out for that number of frames per second just how many nanoseconds does it equate to. Now, you might be sitting thinking, why are we worried about nanoseconds here? It's true, it just depends on the functions where we're getting out the time. We will get a number, long number, which will be nanosecond count. Normally when we're recording or worrying about the time in a game loop, we'll only be working or doing our calculations at the level of milliseconds, not down in nanoseconds. Nonetheless, we work out the number of nanoseconds because this gives us a way of comparing it to the timestamps that we're going to get back. Then we have our update and our draw loop. This is a run method. It's overridden because a runnable interface, you have to provide a run method. That's what a runnable interface needs. And that's the thing, the method that the thread will actually get to execute. So whatever we have in run is what gets to be run on that separate thread of execution. We have a number of variables within this. So just to have a look at these, we have start run, and that will be a counter for the very first time we started running or executing these things. You're going to see that that comes into some of the timing information, that not really visible in this, but in the main game loop, whenever we go to our objects and we ask them to update themselves, we're going to give them some timing information. And that information will be two pieces. One will be the amount of time since you were last updated, and also the amount of time since the game started. And different processes can use that to sort of control activities that are time-based, for example, animations and so on. We have start step and end step as the next two variables. They're going to tie in to basically tell us, well, when did we start doing this update and render, and when was the timestamp when we finished doing this update and render. So that was the total duration. Sleep time and oversleep time. So for these ones here, sleep time we will use to calculate how long we think or how long we want to go to sleep for. So if we had 20 milliseconds to do everything and it took 15, our sleep time would be 5 milliseconds. Oversleep time, now this can be a positive or a negative value. One of the things about going to sleep, if I go to the thread and I say, I want you to sleep for 5 milliseconds, it might get lucky and it may wake up exactly after 5 milliseconds has passed. Alternatively, but because it has to be woken up by another thread and other threads can be doing other things, I might get woken up after 6 milliseconds or 7 milliseconds. I might also get woken up a little bit early after 4.5 milliseconds. So whilst I can say I want to go to sleep for 5 milliseconds, I'm unlikely to go to sleep for exactly 5 milliseconds. It'll either be slightly before or slightly after that I get to be woken up. And I want to take these small errors into account so that next time I go to sleep, I basically, if I overslept, then I sleep for less time this time. If I underslept, I'll sleep for a bit more time then next time. So we want to average these things out. So oversleep time records that error. A few other things, so these are starting things. These are just really initialization to the default one. So our start run, well, we get the time when we started it, and we take away one period from it. So as opposed to having a value of 0, we'll start one frame in the past. It just sort of helps some of the, if we immediately try to take actions based on this, it sort of looks as if we've done one frame's worth of update. Other ones we initialize, those are their starting values. We've got a try process, and the catch is just off the bottom of the screen. So we're going to try to do the following. Now, the reason we're trying is that we might fail to do things, and the bit that can fail is the sleep process. So if I try to go to sleep, I might be rudely awakened for whatever reason. The thread can be interrupted, can be woken up. And if that's the case, then an interrupt is thrown, and we would have to catch it and do something with it. We're not going to, in terms of the catch here, we're basically just going to ignore it. Not the right thing to do. You really should catch your interrupted exception and do something proper, but in this simple demo we're just ignoring that. So whilst we are running, so this is our main while loop. So initially running, if you remember back, is set to where is it? Over here, false. So initially running is set to false. So whenever we come into that, whilst we are running, we won't be running at that point in time. So we'll need to be set to be true for us to be able to be running to go through the thing. So we'll need to make sure that we set it to true before we start this particular process. And if we ever set it to false, then we will fall through the bottom of this process, the run will end, and the thread will come to an end. So these are our processes or ways of getting out of that thread of execution. Now, whilst we are running, what do we do? We want to record, what's the current time? So system.nanotime is actually a fairly accurate way of getting the time on a Java-based system. So we go there and we ask, well, what is the current time in nanoseconds? And we store that. And we store that as the start time in the step. So we remember that's when we commenced this particular step. We then call doUpdate and doDraw. Normally, that's where you go and update all of your game objects and draw all of your game objects. If you remember in this case, the doUpdate and doDraw was declared above, and we're not going to do much. We're just going to log things out for update and draw. So we're not doing much in this one, but that's where we would trigger all of our nice action. So doUpdate, doDraw. It'll normally take a longish period of time depending on the complexity of the game. After we've updated and drawed everything, we then ask, well, how long did it take? So our end time is equal to whatever the time at that point in time is. So this first one will be at the start. We'll go away and do a lot of stuff, and then we'll measure just how long it took us to do all of that stuff. From that, we will work out our start time. And there really is 3 elements to this. Maybe better putting them on one line. Now, if you think about it, end step minus start step, that is the total duration. That's how long it actually took for us to do from the start to the end. The target step period is how long we have available. So if this is, for example, 20 milliseconds, now admittedly we're talking about nanoseconds, these things are bigger numbers, but let's just think about milliseconds. If this target step period was 20 milliseconds, and the end time minus the start time took 15, then target minus that is 5. That is the amount of time that we want to go to sleep for. If it's a positive number, it means we actually do want to go to sleep. Let's assume our target was 20 milliseconds, but when we calculate how long it took 22 milliseconds. So in that sense, we're actually behind. We'd have a sleep time of -2. And what that means is we're actually behind schedule. Finally, though, at the end, we correct for any error on the previous one. So that if in the previous one, for example, we slept in for 2 milliseconds and target was 20, end minus start was 15, that would be 5. We would take away then the oversleep time of say 2, and we'd only try to sleep for 3 milliseconds in this particular go. So that corrects for the previous error and gives us how long we believe we should be going to sleep for. We have a test then. If the sleep time is greater than 0, so this means we can go to sleep, we're waiting, then we go to the thread and we ask it to go to sleep. Now the sleep method, it takes in a time in milliseconds. So our sleep time is currently in nanoseconds. We've got to divide it by 1,000,000. That turns it into milliseconds, and we pass that into the thread. Now as soon as we do this, the thread that's running this will stop for whatever specified number of milliseconds that we have provided. And this particular line down here, it will only get to be called whenever the thread has woken up. So basically it's the time after it. So we ask for the time at this point after being woken up, and we take that away from when we ended it. So this is the actual amount of time that we went to sleep for, and from that we take away the amount of time that we wanted to go to sleep for. And this will give us our error on that particular frame, and we'll bring that into account for the next one as well. The else holds true if sleep time is less than or equal to 0. So if we don't need to go to sleep, if we're behind schedule, or if we're spot on schedule, then we don't do anything, and we set our oversleep time back to 0. So just saying, okay, we've no error in the previous one, we were spot on, or we're ahead of time, so we don't need to do anything about it. And that's really it. We will keep going around and around that process of updating and drawing, working out how long it took, going to sleep or not, and keep on doing that until running becomes false. So that will be an infinite loop until that condition is true. The bits at the bottom then are the things that will change the running flag. We've got a pause and we've got a resume. And if I zoom up to the top just for reference, so you'll remember here that when the fragment got paused or resumed, we went to the loop and called the pause and the resume method. So these are methods that will be called whenever the fragment is paused or resumed. So if we pause the fragment, we want to pause the game loop. So we change our running flag to be false. So if that is false, it means that what is happening in here, as soon as we get down and around to the while for the next iteration, it'll be false. We'll stop, we'll exit out of the loop, and actually we'll quit the thread at that point in time. What we do next here is actually a sensible thing. So, okay, whilst true, we're going to try to join the thread together. We're catching interrupted exception. The reason we have this, and I'll go back to maybe this diagram. Let's assume that the the fragment pauses. So our main thread here does the on pause, and it's going to go to the other thread and tell it to pause. So we're in a situation where one thread is telling the other one to finish doing its update, finish doing its drawing, and then don't do any more. It is good behavior, it's a safe thing to do, that as opposed to this thing just telling it and then carrying on, the main thread should tell it and then wait until it's came back and effectively indicated, okay, I'm paused, I'm not doing anything else. So that's the bit that we have in here. If we try to join the thread, we're going to wait until that other thread finishes its execution. So it'll finish doing its update and drawing, whatever it was doing, and then at that point return to ourselves. You can actually, if you got bored working or waiting, you could put in a delay there. So you could say, I'm going to wait half a second for that other thread to quit out. If it doesn't quit out in half a second, well then I'm just carrying on irrespective of it. But it's a sensible, safe thing to do. At the end down here, the second thread, the thing that was doing the game loop, is not so much paused, it is actually stopped, is exited, it is disappeared, it is finished. So we actually kill the thread, the timing thread, whenever we pause our fragment. Not a problem, because whenever we resume it, we set our flag to be true, and we create a new render thread, and we get it started, so it actually kicks off. So as opposed to pausing the thread, we simply discard it and then create a new one. And because we're not doing that massively frequently, that's an okay thing to do. There's a bit of a cost involved with creating and destroying threads, and if you're doing it frequently, use a thread pool. But in this case, we do it reasonably infrequently that we're allowed to get away with that. So that's really it. We can take the basic example we had before, looking at the different Android states. We can link it in here with a game loop class and tie into the pause, the resume, and use timing mechanisms to update and to draw our objects. So we've got a good bit. What we need to do then is to work out, okay, let's have some game objects that can check for input, that can draw graphics and do things out. So that's going to factor into the remaining demos that we're going to have a look at.